All right, continuing with section 4.1, can we graph a polynomial using its intercept? So here's a polynomial. It's given to us in factored form, which makes graphing it much easier. Okay, so first, what you want to do is you want to find the x and y intercepts. You want to use those and then identify where is the function above or below the x-axis. And we'll see how to do that. It's easier than you'd think. And then with some other points that you can put down on the curve, connect them up with a nice draw. Okay, so copy down the function x minus 3 squared times x plus 4. So to find the y-intercept, just plug in x equals 0 and you get out 36. All right, the x-intercepts satisfy how do I get out 0, and having the function already be in factored form makes this very convenient. Okay. X can either be 3 or negative 4 from the two factors of x minus 3 squared and x plus 4. So it has two x-intercepts, negative 4 and 3. So let's go ahead and figure out what happens in between the intercepts. I wish this slide wasn't quite so full of text. So here's the real number line, and we know that it has some intercepts at negative 4 and x equals 3. The graph is allowed to touch or cross the axis at those points, but only at those points. Those are the only x-intercepts. So if I take a value, let me copy the function, f of x is x minus 3 squared times x plus 4. Okay, so if I take a value of x somewhere in between and plug it in, I'll determine where is the graph positive. So for example, what's a number in between negative 4 and 3? An easy one would be 0. So now I'm going to get negative 3 squared times 4. This was already on the previous slide. This was just 36. This is positive. So at this point of x equals 0, the graph is positive. Here it has an intercept, here it has an intercept, and they're the only intercepts, means the graph has to be positive all the way through. Because it was 0 here, it was positive here, and there were no other zeros for it to have, and it doesn't jump around. The graph is continuous, it doesn't have any gaps. So if it's positive here, and these are the only intercepts, it's got to be positive all the way in between. Okay, so that's the sort of reasoning we're going to use. So on the, let me clear off these pen marks. On the intervals from negative infinity all the way to the intercept of negative 4, it will either be positive or negative. In between the two intercepts, it will be positive or negative. And then to the right of the last intercept, it will be positive or negative. We just have to determine which is which. So we're just going to make a sort of table. Okay. These are the only intercepts. What's really crucial is that we found not just some of the intercepts, we found all of them. There are no other intercepts to be found except for negative 4 and 3. So to determine where the function's positive or negative, we just pick some number in each interval. Okay, what's a number somewhere to the left of negative 4? Negative 5 is a good one. The function, just to remind us, by the way, it was x minus 3 squared times x plus 4. So if you take negative 5 and plug it in, you get out negative 64. So to the left of this intercept, it was always negative or always positive. At one point, it was negative. Therefore, it's always going to be negative. For a point in between negative 4 and 3, the book has chosen negative 2. I'm not sure why. They had already computed what f of 0 is. But sure, if we compute f of 2, we get out positive, so it's above the axis. But then observe, it doesn't just flip-flop above, below. Because to the right of this intercept, we go ahead and plug in 5, and we get out positive 36. So in other words, it's actually above the axis to the right of this intercept. So let's see how that would possibly be drawn. Okay. Yeah, let me go back, because the book just gives you the whole picture without really explaining how they got it. So we know we have an intercept of negative 4, 0. And I have an intercept of 3, 0. We also have an intercept of 0, 36. So I know the graph is going to be above the axis here, but we also computed 5, 36, which means the graph is going to be above the axis here, and we know it's actually going to be below the axis to the left of -4. So from this root, I must go below the axis. Here I must go above it. I must have a root, and then I must go above it again. So the graph has to look something like that. Okay, what isn't immediately clear is the graph goes up and comes back down, so where is this maximum? I happened to draw it right at this intercept, but that's probably not very accurate. I don't actually know where the maximum is. Okay, so the graph could have done something like this. It could have had a higher point and then come down. It could have had a higher point later. Okay, or maybe it was the maximum, I'm not sure. So let's refer to the actual graph. Yeah, the maximum appeared to be slightly to the left of that intercept, but there it is. Okay, as promised, from this intercept, it had to go down. Between the two intercepts, it had to go up and come back down, and then to the right of this one, it went up again because the graph was going to be positive. Okay, so let's discuss what are called turning points. A turning point is where the graph goes from increasing to decreasing or from decreasing to increasing. These are called turning points. If a function, if a polynomial is of degree n, it can have at most one fewer turning points. Okay. Conversely, if you can find a certain amount of turning points and you know it's a polynomial, the polynomial has to have at least one larger degree. So for example, let's take a look at some graphs on the next slide and identify which of these could be the graph of a polynomial. If they could be, find the zeros and use the turning points to state the least degree the polynomial can have. So how about this? Is this a polynomial? No. It's got a gap, it's got one of these discontinuous jumps, and polynomials don't have those. How about this? Yes, this could be a polynomial. Notice it has 3 zeros. It also has 2 turning points. Okay. Because it has 2 turning points, the degree has to be at least one larger, at least 3. It could be bigger than that, but it's definitely at least 3. We actually can tell a little more. Well, we'll get to some extra stuff later. I don't want to get ahead of myself. How about this? Could this be a polynomial? Well, no. It's got one of these sharp corners, which polynomials don't have. How about this? Definitely could be a polynomial. Okay, it has 2 zeros. How many turning points does it have? It's got 3 here, here, and here. So if it's a polynomial, it's got to be at least degree 4. Possibly higher, but at least degree 4. Okay. So let's actually end this video here. We'll make another one to talk about what's called end behavior and finish out this section.